lecture, we discovered some shocking news. It appears that there is a physical limit for the current computing technology. At some point, we will not be able to construct smaller transistors, and the growth of our computing power will eventually stop. This alone can distress us, but there's more. I already mentioned the word universality. Now it's time to dig a little bit deeper, understand what does it mean. And to do that, we first need to define what is the goal of computation. Computation transforms information, that's true, but why? Can we give a general answer to this question? Yes, we can. If you reflect a bit on any computation you ever performed in your life, you will probably agree that you computed the value of some function. Again, it is just another way of saying that computation transforms information because it maps some input data to some output data, and so does any function. So why do I need this another definition? Why do I need to employ this notion of function? Because functions have a strict mathematical definition. I can define, for example, the whole set of functions which transform natural numbers, map natural numbers to one bit. And this set is infinite, but it is well defined. And now I can ask myself if I can compute any of these functions. And for this question to be correct, I have to define first what does it mean that I can compute a function. For example, for the function f, I can compute it if for any x, natural x, I can compute f of x. But there is an infinite number of such inputs, so how can I be sure that I can do that for any of them? And I can be sure if I have an algorithm for computing this function. But I just explained one unclear thing through another. What is algorithm? And the answer to this question was given by the English mathematician, English scientist, Alan Turing, in his PhD thesis in 1936. Algorithm is deterministic Turing machine. Before that definition, there was some understanding that algorithm is something which works for any input data. It has finite number of steps, and it requires no thinking effort. But Turing gave us this strict mathematical definition. So algorithm is a deterministic Turing machine, DTM, and it is, as you probably remember, is an infinite tape marked into squares and the finite alphabet, symbols of which can be written on these squares, and read-write tape head, which can read and write one symbol at a time on each step, and finite number of states, including initial state and final states, and the finite number of rules which control the behavior of this abstract model. So now, algorithm is a finite tuple of finite set and set elements. And this is a very powerful model because it allows us to define the universal Turing machine, which is the deterministic Turing machine, which accepts another Turing machine as its input and emulates its behavior. So this universal Turing machine can do anything that any other deterministic Turing machine can do. And around that time, in 1936, a hypothesis was formulated, which is now known as Church-Turing thesis, which states that there is no other deterministic computing device with a repertoire larger than that of the universal Turing machine. So now this question, if we return to the question of computability, now this question about these functions which transform natural numbers to 1 bit. Now this question makes sense. We can ask ourselves if all these functions are computable, and we can try to reply to this question. So are they computable? Because for any function to be computable, now it means that there is a deterministic Turing machine which computes this function. And to answer this question, we first need to, we'll count how many deterministic Turing machines are there. Of course, it is an infinite set, but we are going to find out which is the cardinality of this set. And since any deterministic Turing machine is a finite tuple of finite sets and elements, it can be encoded as a finite string in some alphabet. For example, in the alphabet of ones and zeros. So any deterministic Turing machine we can represent like this. Some finite string of zeros and ones. And any of such strings can be mapped to two natural numbers. First is the number of leading zeros, and the second is the number represented by this string in binary encoding. And this set is countable, so now we can conclude that we have only a countable infinity of deterministic Turing machines. Sounds good. Now let's compute how many functions of this type are there. And to do this, we are going to define the following procedure. I will take some function from this set, and for this function I'm going to write a string, again of ones and zeros. I'm going to write 1, 0, then decimal comma, and then I'm going to write one bit which is f of 1, the next bit is f of 2, f of 3, etc. up to infinity. And this infinite string of ones and zeros represents some real number on the interval from 0 to 1. And different functions map to different numbers from this interval, and different numbers from this interval define in this way different functions. And we perfectly know that there are continuum of such numbers, of real numbers on the interval 0, 1. So there is continuum of these different functions of this type, which means that there are uncomputable functions. And even more, if we take a function from this set at random, then the probability of the event we can compute it is 0. We can compute almost nothing in this mysterious and beautiful world. Okay, maybe it's not so bad. Maybe all these uncomputable functions are bizarre and useless. It appears to be not true. In the same paper where Turing defined this deterministic Turing machine, he provided us an example of a very useful function which is uncomputable. And this example is now known as the halting problem. Imagine a function, for example, we'll call it hash, which takes a deterministic Turing machine, some algorithms as its input, and the input for this deterministic Turing machine. And this function returns 0 if this machine will eventually stop on this input at some point of time and provide us some result. And it returns 1 if this Turing machine hangs on this input. So for this input, it has some infinite loop. So this function, hash, it analyzes in some way the machine on its input and gives us an answer if it has an infinite loop for this particular input or if it does not. And Turing proved, and it is quite an easy proof, that this function hash is uncomputable. So it means that deterministic Turing machines cannot analyze deterministic Turing machines. And if Church-Turing thesis is correct, then we are deterministic Turing machines, and we are not able to analyze every computer program. Which means that there can be written a computer program which we will not be able to understand or to predict its behavior. A deterministic computer program. Isn't that amazing?